But that's the whole gist of what we're doing today. This is the last we have today, and actually I don't know if I'm going to be I'll probably be here on Monday of next week. Because this is the weird part where my work schedule is offset from your spring break. College's spring break is next week. They had finals this week, and their spring break is next week, and your spring break is the week after that. So everybody's schedules get really wonky here for a little bit. So I think I'll be able to make it on Monday of next week. But point remains, next Thursday and Friday is going to be when you take the midterm. So last big topics before the midterm are stoichiometry, which we're going to practice today, and a subset of that is basically we're just adding concentration units, and so that's probably what we'll spend the most time on Monday. It's just finalizing that. So we'll start by just a bit of a review. We talked about hamburgers. Yeah, Maddie. So because Friday's the minimum day, my plan is that, and usually I allow for 2 hours to take the test, but you don't have 2 hour time blocks in midterms. So what we'll do is problems 1 through 6, parts 1 through 6 of the test will be on Thursday, and then 7 through 10 will be Friday. Melissa? It will not be open note, but you will have a fresh conversion sheet and periodic table, and that's just as good, right? If I made it open note, you wouldn't have time to look anything up anyway. There's just enough time pressure that you've got to know the stuff pretty well. I toyed around with doing open note tests, and actually the class average goes down on those because people don't finish in time. So in general, it's for your own good that I'm making you practice on the practice tests and just learn those concepts. But remember, there's not going to be any surprises, right? So just work on that practice test, which you got yesterday? No, Tuesday. And I think the last concept that you haven't seen on the practice test is concentration. Which I guess we could do before we jump into stoichiometry. We can do that so that because it does show up at some points in here. Does anybody know what concentration is? Besides focus?
How many are in a specific area?
How many things are in a specific area? That's not a bad way to think about it.
The amount per unit, like the amount of stuff that's per.
You're both right there. It's the amount of stuff, not per area. Technically, if it's in 3 dimensions, it's per volume. Although you could technically have a concentration. I don't know if it would be considered concentration, but if we said how many dots are there in 1 square foot, you could count those up. I actually didn't count them when I dotted them on there, but it looks like it's about 10. So it would be 10 per square foot. You could consider that a concentration. Concentration at its most basic is just how much stuff do you have per unit volume. All right, so there's a lot of different ways we can do that. Can you think of any units, common units for concentration? Parts per million. That's a good one. So parts per million just means if you have 1 million of something, let's say 1 million gas molecules, that's 15 parts per million means 15 out of every million are going to be a certain molecule, a certain compound. So parts per million is definitely an example. And one of the ways I look at this is basically how are the ways that we could measure if concentration is an amount over a volume. It's almost like a percentage where we can think of what is the part divided by the total. So what are the different ways we could measure amount? What units would we use if we were measuring amount of something? Moles. Moles is a perfect one. Mass. So this 3x3 grid
It's actually gonna be the same variables on all three. These are the most common ways we measure an amount of something. We measure an amount in terms of moles, we can measure an amount in terms of mass, we can measure an amount in terms of volume. Which means I wrote volume down here, but if we say, if we think about this like a percentage, and it's really part over total. Part over total is another way of thinking about concentration, right? Not if it's not necessarily volume, we could put moles, mass, or volume for the part, and we could put moles, mass, or volume for the denominator as well, right? So basically, concentration is just a way that we can have this ratio. And sometimes it is a percentage, and parts per million is actually an example. It's not a percentage, because what does percent mean? Over one out of 100, right? Parts per million means out of 1 million. So parts per million and percent actually mean the same thing. And actually, literally, they work the same way, because parts per million versus percent break down percent in terms of Latin. For every 100. It literally means for every 100. So parts per million is literally the same thing. We're just multiplying by a different number at the end. Right, so if we looked at how many moles of one particular piece, one particular compound, there were over moles total, that's one way we could measure concentration. Ace?
Wait, percent is per 100, like we use different Latin words, we get like what's for per 10%.
They're not commonly used, but technically, yeah. There's probably a it's not percentile, it'd be the per decile or something like that. Decile per decile would be if you did it out of that 10 instead of out of 100. Percent, for whatever reason, is just the one that we use the most, but it works the same way as any other ratio, right? So the most common concentration we're going to use in chemistry is if we measure how much of something we have per volume, per liter. So this is what we call molarity, is how many moles of solute you have per liter of solution. But you could do moles of solute per moles total. Then we'd get a ratio that looked a lot like a percentage, right? Like a percent by mole. But you could also do a percent by mass. What does percent by mass look like? How would we measure that? What would it mean if I said something was 92% by mass? Like, yeah, let's say if something is 92% sugar by mass. That just means that for every 100 grams of the mixture, 92 of those grams are sugar. Right? So we have all these different concentration units, all these different combinations are just going to be different ways of looking at part divided by total. And if you want it to be a percentage, you then take that and multiply by 100. Right? Moles of one compound over moles total actually has a shorthand as well. So I guess moles of something over total liters, the shorthand for that is capital M as a unit. It's called molarity. That's the most important one you need to know for this class. Right? Because that's 9 times out of 10, if you get a concentration in chemistry class, it's going to be molarity. That's not always the easiest way to make a solution, though, necessarily. Right? Because it's not easy to measure moles directly. If we're trying to measure moles of something, how do we usually do it? Somebody already said molar mass, right? You weigh out how many grams of something there are, right? If you're reading a recipe and it's trying to tell you how to make
I don't know, simple syrup. Anybody ever made a simple syrup before? How do you do it? Sugar and water. You need a ratio though, right? You need a certain amount. Do you know what that is? 1-to-1 by volume, right? 1 cup of water for 1 cup of sugar. So that's a concentration here. That's just like a 1-to-1 ratio. That is a concentration. We're just measuring our part in terms of cups or in terms of volume and our total in terms of volume. Right? So the other way that you might do it be like if you're in the UK and you're baking, anybody watch British Bake Off? How do they do all of their baking in British Bake Off? They don't use cups, right? They do everything in what? In grams. So if you're measuring a concentration, trying to give somebody direction in a baking recipe, it'll be measure out 14 grams of sugar and dissolve that in half a liter of water. That's a concentration too, right? Grams per volume. So you can have grams per liter as well. And those are really helpful for giving instructions, like in a baking recipe, but also if you're trying to make solutions in the stockroom here. Yeah, every time we do a lab that has solutions, somebody has to make those solutions, right? Which, if you're doing a lab here, it's mostly Tom's. If you're doing a lab at the college, it's our lab manager Mariola. Either way, it's a lot easier when you're making a solution if you have instructions that say, take 50 grams of barium chloride and dissolve it in 1 liter. That is also a concentration unit. Your concentration is now grams per liter. Right? So it's always going to come back to just a part divided by the total. And most of the time, the easiest calculations are going to be in moles per liter. Right? And we want to be careful when we abbreviate these units. Capital M as a unit is molarity, is moles per liter. Moles of one component divided by liters of solution. Right? And to get from any one combination of concentration units to another, it's just a quick conversion usually. Maybe a little bit of calculations involved. But for instance, let's use the example I just made. Let's say we had a solution that was 50.0 grams of barium chloride. And we put that in, let's make the math more interesting, 0.500 liters. So it's already in concentration units, right? It's 100 grams per liter is the concentration. But if we want to put it in molarity, how do we do that? We're already in liters here. Molarity has to be moles divided by liters. So we've got our liters. So we want to multiply by it. That's why I would always write it out as those t-squares or conversion factors. We want to cancel out grams to be left in moles, right? So we take our atomic mass here. So for barium chloride, I probably could have picked something that I actually know the masses off the top of my head, but 137 for barium and then 2 chlorides is another 70. So it's going to be something right around 207. The 3 sig figs, I think that's about right. It might be 208. It's 208. So we get something that looks like, what about point 2 what?
2, 4, 0. Well, how many sig figs?
3 sig figs.
Yeah, 2, 4, 0.
So once we know moles of barium chloride, we want to put it in molarity units. We just take the moles that we have and we divide by the volume that we have. in liters. So we're going to multiply it by 2. So our molarity is going to be 0.480 capital M for our unit. Capital M means moles per liter. The other way that we write this, because this also doesn't say moles per liter of what. Right? So the way that we express that this is concentration of something in particular is we put that compound in square brackets. Square brackets means moles per liter. Or concentration, but since we always do our concentrations in moles per liter. So if you have concentration units that are not moles per liter, you just do some conversions. Similar to the way that we, if you think back to the way we converted miles per hour into meters per second, we just took the miles section and we converted it to meters, and we took the hours and converted it to seconds. Everybody remember doing that? We do the same thing here with concentrations. If you get a percent by mass, you can do the same thing. You might have to get creative with some of the conversions, but it's always just a conversion. If you have a concentration unit, getting to another concentration unit just takes a little converting. Almost always, this is where we're trying to go. It's moles per liter. All right, so let's do another version of that before we actually, let's look at the practice test. Let me pull up the practice test real quick, because there was exactly one problem where this showed up on the practice test, right? Is it number 8 or 9? Number 8, thank you. So we have a reaction where instead of being given in grams, we're given a volume of solution and a concentration. So for all these stoichiometry problems, first step is always balance, right? The second step is always put everything that you can in moles, because we can't do stoichiometry with things in grams, right? Because we balance it in terms of atoms, so we need to put everything in terms of moles in order for stoichiometry to work. So we're trying to figure out how many moles of sodium hydroxide we have based on a starting concentration and a volume. How can we figure that out? So 250.5 milliliters at 0.105 molar, and that's shorthand for what? Moles over liters, right? Which makes it a combined unit, right? Concentration units are combined units like densities or like speed, right? So the same way that we could use 65 miles per hour to convert a distance into a time, we can use a concentration to convert a volume into moles. So if we know that this is really moles over liters, that just means we need to put our milliliters in terms of liters, and we can use our concentration as a conversion factor, just like with the density. So we can say, okay, 250.5 milliliters, put that into liters. For every 1,000 milliliters is 1 liter. And once we're in liters, we can convert straight to moles. So it's actually easier to get to moles from a solution, from a molarity. That's why we write down these concentrations and molarities. Because it's actually easier. We don't even need to use a periodic table. We don't need an atomic mass. All you need to know is what your starting concentration is. Because then you can say, okay, for every 1 liter, that's 0.105 moles. We'll get something like 0.0255 263. So the trick here, this big skill to take away from this in terms of what's going to show up on the midterm next week is you need to be able to use a concentration to get to mole. You might see something show up in terms of the wildcard question where I make you calculate a concentration, like we started with the barium chloride example or something like that. Molarity is also a good one for me to ask about in the vocab section on the front page. I'm just going to pick random concepts to ask you about on the front page in part 1, right? I'm not going to go like anything really super niche or anything like that, but something like concentration. Explain in your own words what concentration is or what molarity means would be a good thing for me to put on in number 1, right? But the one place that you absolutely know concentration is going to show up is right here. Be able to go from a concentration to moles, or from moles to a concentration. Now you have everything you need for the test, so you're ready to take the test now, right?
Yep.
Lucky for you, you still have a whole nother week practice to get feeling pretty good about that. So let's do some of that. The rest of what we're going to do today is just practice with stoichiometry. The key is always balance the reaction. Then if you're not given something in moles, you're going to convert it to moles right off the bat. From there, it's just a matter of, am I making something or using something up? What is the question asking me? All right, so let's start with this one. Everything's already in moles, so this is a good warm-up. So we got aluminum reacting with bromine to make aluminum bromide. If I'm naming this, do I need a Roman numeral for aluminum? That's one of those 6, right? Aluminum doesn't actually have a D block, which means it actually behaves the way it's supposed to. It has an empty D block technically, but. All right, how are we going to balance this? Got an even number here and an odd number there. So right off the bat, we know something, right? What do we have to do? We're going to have to double this. Which means we might as well double the other aluminum too. That keeps our aluminums balanced, right? And then that gets us to a total of 6 bromines on each side, 2 aluminums on each side. So if we have 3 moles of bromine, and remember, I will stress this again, don't abbreviate moles as capital M. They mean 2 different things. When you're getting lazy or in a rush, it's really tempting because what's the whole point of abbreviating mole by dropping 1 letter? Does that really save us much time? No. But we can't abbreviate it any further without causing confusion. So don't write capital M as your unit there. So if you wrote it like that, I mean, it's better than not showing any units when you're showing your work, but I prefer you write MOL for all of them. If for no other reason than if you did that, it's easy to confuse yourself, especially if you're going to have to turn around and do some conversions with it. Because wait, I wrote 3.0 M. Was that moles or was that meters? I don't remember. Right. So the main thing is making sure that you get your final answers in the right units. But as we get more and more complicated questions, it gets harder and harder to keep track of that. So if we've got 3 moles of bromine, and that bromine's going to react. In other words, we have 3 pieces of cheese, and we're making a hamburger with it. How many pieces of bread do we need to use up 3 pieces of cheese? This is why it gets tricky when it's chemicals instead of hamburgers, right? And this is why we show our work for it. Even though when it's food, it's easy. We know we can do that in our head. If we want to show our work here, we say, okay, well, if I have 3.0 moles of bromine, every time 3 moles of bromine is used, that's 2 moles of aluminum used. Right, that's the whole point of balancing this, is it tells us the ratio, the relative rates that they're being used up. If you use 3 bromines, it's going to use 2 aluminums. We show our work like this, right? Because now moles of bromine cancels out, and we're left in moles of aluminum. And in this case, the 3 is going to cancel out also, right? It won't always be nice numbers like that. So it's easy to get to 6 from this by doing 3 times 2, right? You got to remember that coefficient goes on bottom as well. Right? When you're doing these stoichiometry steps, you need to pull the coefficients right out of the balanced reaction. So let's do it a little bit that's not as kind of numbers. How many moles of bromine does it take to react with 1 mole of aluminum? So same reaction. The question is, okay, if we have 1.0 moles of aluminum, how many moles of bromine? You just write it out the same way, right? See whether we're supposed to multiply or divide by the coefficients. You have to write it out as a conversion factor. Because every 2 moles of aluminum is 3 moles of bromine used. So we're just going to get 1 times 3 over 2, 1.5. So to go back to our hamburger analogy, it takes 2 pieces of bread to use 3 pieces of cheese. I guess maybe this is a grilled cheese, not a hamburger. If it takes 2 pieces of bread and 3 pieces of cheese to make a grilled cheese, how many grilled cheeses can you make with 1 piece of bread? Or how many pieces of cheese are you going to use? 1.5. You have half a sandwich worth of bread, right? You have half a sandwich worth of bread, you're going to use half a sandwich worth of cheese. This is how we show our work for that, though. Balance the reaction, write it out as a conversion. I don't care if it's in parentheses or t-square, whatever, however you do your conversions. Doesn't matter to me. Right, so there's a lot of different types of questions I can ask, right? I can these first 2 parts were both asking about the reactants. How much of a reactant is going to be used up to use up all of the other reactants? But I can also ask about how much product are we going to make? If we want to make 8.51 moles of product, how much bromine is required? Is there anything different about that, really? Just the words used versus produced. But other than that, the steps are going to be the same, right? If I want to make 8.51 hamburgers, grilled cheeses, moles of ALBR3. If you still want to put it in food terms, you can't have 8.51 grilled cheese sandwiches, but you can have 851 grilled cheeses, right? So you could think of it as how many pieces of cheese do I need to use to make 851 grilled cheeses? 2 moles of product means we use 3 moles of cheese. So divide by 2, multiply by 3. So 12. 4.25 times 3, 12.75. 12.778. 76. Doesn't matter because it's only 3 sig figs. 12.8. Right, so it seems like there's lots of different ways I can ask these questions, and there's lots of ways I can phrase these questions, but the math is the same every time. Right?
Does it matter how they have different amounts of bromine in each one, or is it just literally moles to moles?
It's literally moles to moles. It doesn't matter because we balanced it. If we didn't balance it, this doesn't work.
You get that one? Sorry, say it again. You get that one? Ask the question.
He got you.
Yeah, for sure.
Michaela.
How would the supply be defined on the practice? It says excess, but
So let's look at another one from the practice test. That was 9. So the other way that I can ask this, and this will make more sense in a second why we have to write it like this. In some cases, we have to worry about what we're running out of first. So if I said we had 2.7 moles of bromine and 1.5 moles of aluminum, it's not immediately obvious what's going to run out first. Are we going to run out of cheese or bread first when we have some amount of both of them? It's not always obvious, right? Sometimes, though, we're not worried about it. So in this case, this problem is specifically saying you don't need to worry about running out of HCl. It's excess just means you're not going to run out of it. So in this case, what this question is asking is, okay, you're never going to run out of bread and you have this much cheese. How much sandwich can you make? Right, so it's saying how much product in grams can you make based on these conditions. And this is actually the easier case. We don't need to worry about what's running out first. What did we call the thing that we're going to run out of first? Limiting reactant, yeah. So limiting reactant is just whatever runs out first because that's going to dictate where the reaction has to stop. We can't keep making grilled cheese once we run out of cheese.
You just make grilled.
We just make grilled. You make toasted bread, which is still delicious, but. So in this case, this is another good warm-up. What's going to run out first? And what's our theoretical yield
how much product can we make? We're not sure what the limiting reactant is, though. So the way that I typically approach these questions for this, the way this question is asked, where it says, okay, I don't know what's going to run out first, but I want to know how much product I can make. You just, the way we can do it mathematically is to say, okay, well, I have enough aluminum to make this much product, and I have enough bromine to make that much product. One of those is going to be the right answer. Right, so if I have 1.5 moles of aluminum, and every 2 moles of aluminum is 2 moles of product. So 2 over 2, 1 over 1. So we have enough aluminum to make 1.5 moles of product. Is that our final answer? It's one of our answers, right? Now we do the same thing with our other reactant. We have enough bromine to make, so put 3 moles of bromine on bottom. For every 3 moles of bromine, we get 2 moles of product. So divide by 3, you're going to give us 0.9, so we get 1.8. So 2 questions. What runs out first and how much product can we make? I have aluminum and I have bromine. How do we decide? Put it in terms of hamburgers. We have enough patties to make 15 hamburgers, and we have enough buns to make 18 hamburgers. So we're going to run out of patties first, right? How's soundproof on these walls? I just realized I knock on the board a lot. I'm wondering, can you hear that next door?
I hear them not.
Okay, I'll try not to do
I
that.
don't know you playing, so.
All right, so we answered 2 questions at once here. We know that aluminum is running out first. That's our limiting reactant. And we know how much product we can make. And that we call our theoretical yield. What does yield mean? Yeah, it's another word of saying produced. Right, so it doesn't mean yield in the traffic sense. Yield just means how much it produces. So if everything went perfectly and you used all of the aluminum you have and every molecule of the aluminum went to making product, which never is the case, but if everything went perfectly, we could make 1.5 moles of aluminum bromide. So number 9, or I guess let's go back on the practice. Number 7 is this exact same question. The balancing is going to be different, but it gives you an amount of both of your reactants in moles already, so you don't even have to convert to moles. And it just says, how much product can you make? So you're going to do the same exact thing. I have enough barium hydroxide to make this much lead 4 hydroxide. I have enough lead nitrate to make this many moles of product. Which one's going to run out first? How much product can I make? Right, so literally all that's changing is the balancing, is the numbers. I mean, technically the chemicals are changing too, which is why the numbers are changing, but it's the same process of what we just did.
seem relatively straightforward, as long as I'm the one with the marker. Well, good, then we're gonna make it more complicated. And you will get the key to the practice test as well, so you'll be able to check your answers even if I'm not around. Explain it to everybody else, that kind of thing. I just erased that reaction. I'm gonna rewrite it. Because one of the only ways I can make these questions any trickier is by not starting in moles. That's just a one-step conversion, right? If you're given a mass, then you use your molar mass. If you're given a concentration and a volume, then you do that concentration calculation that we just did. And so 2 aluminum plus 3 bromine reacts to make 2 aluminum bromide again. So in our food analogy, this is just like, okay, I don't tell you how many slices of cheese you have. I told you how many pounds of cheese you have. So how many grilled cheese can you make? Well, first you've got to figure out how many slices you have based on how many pounds you have, right? So if we have 25 grams of aluminum, we want to know how many moles of product we can make. If it's not specified, you can assume that you have excess of your other reactants. On the test, obviously, I'm going to explicitly say excess, but the way this question is written, if you don't have any information about bromine, just write assuming that we have excess bromine. Assuming we're not going to run out. So 25 grams of aluminum. If you see what the steps are, you don't have to break it up and get to moles and write moles here first, and then do moles to moles calculation. You can do it all in one calculation. But not everybody is going to see that as quickly. The 26.982, I think. Gives us moles of aluminum. Point 92927. So we want to know how many moles of product we can make. Now we're in a spot where we can do our stoichiometry conversion, right? This one, that math is easy. Because the aluminum and the aluminum bromide are 1-to-1, right? What if I change this to make it instead of moles? We've made it grams. We had grams of aluminum.
Oh,
We know that the moles of aluminum is the same as the moles of aluminum bromide, but the mass of aluminum bromide is not going to be the same. All right, so if we have 0.927 moles of aluminum bromide, now we just need another atomic mass, right?
Bromine's big. 26 point, let's say 982. Plus 3 times 79-ish. 266.7.
I just asked one of the questions using the month as a unit, and I assume that month is the 31 days.
You can assume that a month is a 12th of the year,
All right.
and you know how many days are in it. So that gets tricky because there's a lot of uncertainty. There's more than one day of uncertainty in months, right? Incidentally, month is the reason why you can't abbreviate MO. MO is month. So what you can do is if you have months, we can't say it's 31 days in a month. We can say that there's 12 months is 1 year. And then we can say 1 year is 365.24 days. So, and actually, if you did that math, if you took 365.24 divided by 12, you would get days per month on average. And if you could use that number if you wanted. Isabel? Let's talk about that 0.24. This is one of my favorite examples of uncertainty. There's 365 days in a year, right? Mostly. What happens every 4th year? And what happens on leap year? We get 1 extra day, right? You'll notice that's really close to a quarter. For every 4 days, we build up 1 extra day. But it's not exactly a quarter. It's off by 100. Which is why every 100 years, we skip leap year. And exactly. And then, and it's 3.24. It's really close to 0.24. So basically, every 4 years you get an extra, except every 100 years you don't. Will work for the next 1,000 years or so. And if we're still worried about that, then we've done a good job, and we'll have a better way to figure it out by then. Right?
If you had a question on the midterm that was relating months, would you expect us to use that conversion?
For full credit.
65.
And you'll notice on the conversion sheet, there is no days to months conversion. There's months to years and years to days. So if you stick to what's on the conversion sheet, then you don't need to worry about it. You'll be given the conversion sheet. And periodic table. How we feeling? Okay. I was in a class that was a even longer lecture than what you have to deal with. It was a 4-hour long lecture. There was activities and stuff in part of it, but the speaker brought a bunch of fidgets and clay and pipe cleaners and just put them in the middle of all the tables for people to just play with. And that was a lot of fun. It was kind of fun to have something to do. It's not something any of my professors ever thought to do when I was in school. So if fiddling with the molecular models is helpful for you, then by all means. All right. So we talked about we talked about limiting reactant, and we talked about theoretical yield. There's a couple other key concepts, and that's all the stoichiometry we need to deal with for right now. One of those key concepts is the idea of leftovers. We call leftovers excess reactants, and sometimes we actually care not just
what the excess reactant is, but how much of it is left over. If we're making 851 grilled cheeses, and we're gonna have several thousand buns or pieces of bread left over, we'd kind of like to know that we're gonna have several thousand pieces of bread left over, right? So sometimes knowing the amount of excess winds up being important. So for this reaction, iron rusting. How much excess reactant is left over? We did this with hamburgers on Monday. Let's do it with chemicals now. Can you tell just by looking at these what's going to run out first? It takes a little bit of practice. These numbers are big enough that's not super close, and they're kind numbers, right? So you might be able to look at this and say, okay, I have twice as much iron as oxygen, and they're being used up at a 4-to-3 ratio. So we can guess without even doing any math that iron is going to be what's left over. We have twice as much iron and we're not using it up twice as fast. So this, if we're going to calculate this, how should we go about doing it? We can do the same thing we did before, where we figure out the theoretical yield by saying, oh, and figure out what's going to run out first that way. But we can also say, if we're pretty sure looking at these numbers, I'm pretty sure we're going to run out of oxygen first. We can say, okay, well, I have 1 mole of oxygen. Calculate how much iron is going to get used. Because for every 3 moles of O2, it's 4 moles of iron used. So divide by, so 1.3 moles of iron used. So there's 3 possible outcomes. We're just kind of guessed which one of these to start with, right? There's 3 possible outcomes. We calculated 1.3 moles of iron used. Do we have 1.3 moles of iron? Yeah, we have 2 moles of iron, right? So outcome 1 is we say we're using less than we have. That's the ideal case because that means that we guessed right. And then we can just say, if we want to know how much excess we have, we can say, okay, well, I started with 2.0 moles and we used 1.3. So we should have 0.7 moles excess.
Excess reactant in moles.
Depends, if I don't specify a unit, then moles is fine. If I say how many grams of iron are left over, then I would want you to go the 1 step further. That's our answer right there. The most complicated way I can ask that is number 8. That's the wrong one. That's the one in your packet? That's the one I was looking at. Is this the one you had? Yeah. So, in this case, this is about as complicated as an excess reacting question can get for now. Because it says, what is the final concentration of excess reactant. So, but that's still really just a units question, right? Figure out how many moles of excess reactant you have and put it in moles per liter. And that's about as complicated as that can get. Figure out what you have left, divide it by your total volume. In this case, what is the total volume going to be at the end? What is this question actually saying? You're taking 250 milliliters of one solution and 275 milliliters of another solution, and you're mixing them together. So what's your final volume? Yeah, we're gonna have to add them together. And so sometimes you have to think about a little bit of the logic, the logistics of it. Not quite logic, not in the writing formal proof way. It's like, okay, well, what's actually happening? I'm mixing two solutions. I have a new final volume now. Yeah.
And the polarity again.
We wouldn't add the molarities because the molarities changed. So the reason that this is a tricky question is because we have starting molarities of both of these, and then we mix them together, and then they react and use each other up. So we want to know what's left over and how many moles of it are left over. So we're not just going to add the concentrations together. We actually have to do this process. Figure out how many moles of each of your reactants, how much is going to get left over, and then take the leftover amount and divide by 500 by the added volumes. Again, it's one of those things where the logistics of it is not that bad when we're talking about hamburgers and grilled cheeses. But when it's chemicals and decimals instead of discrete objects that you can touch, it makes it seem trickier. I just always want you to come back to, okay, what is the logic of this question? Is it a leftover question? Is it a how much can I make question? Is it a what's going to run out first question? Right? Think about what the question's actually asking you. It's always going to be one of those. Basically, this is as complicated as stoichiometry is going to get in this class. We'll add one more wrinkle, which is a different concentration unit when we talk about acids later. We'll bring up pH. But pH is really just another form of concentration unit. So it's one extra step. So this is an example of what's called a reaction study. Here's a very specific reaction. You have specific amounts of everything, and the reaction happens, and we actually get 3.52 grams product. What was the limiting reactant? What's the excess reactant? What's the theoretical yield? And what's the percent yield? The only one of those we haven't touched on yet is percent yield. How do you suppose we get percent yield?
Oh, that's right.
How do we get percent of anything? Part divided by the total times 100, right? So what's the part in this case and what's the total? I like that answer. Theoretical yield is your total. We actually have to do some math before we can get that. Just the same way, think back to doing our first spreadsheet assignment. Before you could actually figure out what the overall grade was in a category, you had to total up the points for that category, right? Before we know what our percent yield is, we have to figure out what our theoretical yield is. All right, so let's give this one a try. By the time we get done with this one, we'll probably be done for the week.
We're close to it.
But I've been doing enough board work up here, so you all do this together. And what we'll do is we'll make this an assignment. So in place of having a quiz over the weekend, this will be your quiz. Still submit it over the weekend, and everybody who's not here is going to have to do it over the weekend. But you can get your quiz done in the next 15 minutes with help. Right, and I'll repost it if you don't have it in your notes. I'll put this in the quiz. But it'll be the same problem, same numbers. Whole thing. No, because that assumes that they're already in the right ratio. If they were in the right ratio, moles, then you'd be able to do that. What you're assuming when you say that is that when you run out of titanium, you also ran out of fluorine at the exact same time. So just that there's no electrons, right? I see where you got to. I wasn't sure where 4 came from first. It is, but that doesn't mean that you had your starting materials in the right ratio. It just means for the starting materials, you have and if they do happen to be perfectly aligned, then sometimes, yeah, you might use all of them. But it's pretty uncommon.
Yeah.
So let me react. What's the other word for that? Excess is how much is left over. Limiting reaction is what's going to run out. What you're going to run out of product. Exactly.
Okay, so you have.
Okay, that'll be it. And ask a question.
Okay, so.
Yeah. Yeah, I'm gonna take this slide and put it on with this question on it. Just take a picture.
Just do this.
Just, there's a lot of those. You don't have to try too hard for that. Something comes through.
You do it.
Yeah,
I don't think it's as bad as giving you.
your.
So everything is great teacher guidance, yeah.
But then also need to say what's going on.
Yeah, teacher department is good. That's the real. It's better. You feel it.
You guys very fine. What about? What about? Why not? Is it plus or minus now?
Not good, Mr. Bell's.
That because balance with actual counting, right?
You rate it?
So that is.
Oh, do I remind me not to make that racist comments? No, no, it's
Yeah, but it's
It is like, for example, if somebody has been walking, you get out, you will have it, and then. Or sometimes.
Okay.
I don't know, I don't know, like, do what, yeah, like, my girl sometimes.
Make the units work out. So number eight, theoretically, you're saying actual. So you want the
So yes, you will want to dividing by the atomic mass, but what you show is so that the gram stands straight up.
Yeah, but.
So that's how it.
Because I know what I'm doing.
No, maybe not unnecessary math.
Hello, did this solve?
Oh, why is your fancy? That's crazy. I just decided.
You're gonna have the whole order of magnitude on the bottom.
That's how many poles I take you out to work.
Oh, oops, but we have to multiply that too, right?
It seemed like
You did. I would keep another sigma though. But yes, remember that zero in front doesn't count.
The ratio here. Because it is not a ratio. Yes, you're right.
Yeah.
Do another.
This is your point of product. That's everyone.
Two volt, back to.
Yeah.
We only have one. Two sigmas.
Yeah.
Well, how much access you're getting the numbers from the ratio. Well, yeah, we got how much.
Oh, no.
We only have one. Yeah. You have too much. You're right. I don't use it. Wait, CI, make sure right at 4. Oh, yeah. So how many moles is this?
So region semi-right.
Okay, I was like, I step.
I don't remember.
Yeah.
So if you know that you're
Oh, yeah.
figure out how many moles of gas medium. Yes. And wait, this actually has.
So you're gonna use up all of your fight and still have 2 0 0.
You need the papers.
I told you, so you're literally.
Thank God I don't have it.
I see, I told you. No, I thought you said 2 is.
And it's really, oh, that's really fun. Yeah. It's like, it's actually, one more. There's 2 chlorine per month.
Wait, so this is the one that we
Better one's good.
I appointed.
We got, course, you're gonna have to use yesterday.
Oh, yeah.
Class next year. This is our 104 is like we read them out.
Figure out.
I don't think we do.
Which is.
It's actually CHM100.
Wait, is it?
Yeah.
It's very short on
Okay.
staff here.
Right.
We don't have teachers, Bill, on someone down. It's 5 sections short on teachers.
How do you get left if you multiply by 2?
So that doesn't have a big ass.
Yeah. So like also our, we need another teacher, that's why I keep pushing.
I mean, then you take, I guess, abortion does not quite severely.
Yeah, but.
It's all because it does. They use that, that's for that should be that big, it's more, the more students who get enrolled in these classes, the more.
Thing is, like the way enrollment works at the high school, we get the money regardless. Of course,
Yeah.
we just need them to take 2 classes.
Is there anybody reacting to an answer and models or correct?
I mean, we did find it, that's fine.
You like.
Actually, we're not reacting. That was just. So you don't. I'm saying for like. So your excess, yeah. It's for the. Yeah. You. Right.
Oh.
Yes.
Which I tell you.
Yeah. And then. There's 2 more.
If you get this, or I know it to have that, guess right.
Yeah.
This.
It's also. This is.
Okay, this is fine. You're not.
That's
That's a lot.
Is there?
I should use. All right, yeah.
No.
So, once I. Even with that in mind. All you got for right? Yeah, but right, so you have 0.05, 0.04. Yeah. Yeah, so if you say 0.04 moles of fluorine, every 2 moles of fluorine is 1 mole product. That's going to give you a number, right? For how much product you can make.
Yeah.
You can do the same thing for the other one, right?
This is why.
Right? And so you'll get two numbers. You have enough fluorine to make 20 hamburgers, and you have enough titanium to make 50 hamburgers. So which one is the real theoretical yield? That tells us that fluorine will run out first, and it also gives us our theoretical yield at the same time, right?
Yeah, so we realized early that these animals actually yield the, so which one would you try?
So which one actually
Shoot,
either a Sp2025 or
It'll be the same. So it doesn't really matter.
Figure out how much it's
You don't understand what you get.
See you guys.
Okay, bye.
Here's my
Yeah.
everybody's here. Yeah.
Oh my God.